In this video, we're going to solve a problem in structural mechanics using the finite element method and FEniCS. It will be the situation of a clamped beam that is under the load due to gravity. It will only take us around 100 lines of code in FEniCS. Then you can execute the file and it will produce some files that can be post-processed in Paraview. Here we will then see how the beam is deflected, including the displacement vector field, as well as the deformed state, including a color plot of the FEniCS stresses. So let's get started. Hi and welcome to this new video. Structural mechanics is one of the classical applications of the finite element method. It allows us to investigate how structures deform under certain loads. For this video, we want to look at one of the simplest cases one can solve here. And for this, we have the following set of equations. The first is the Cauchy momentum equation. Here we will look at the steady state problem. So it will just be the negative divergence of the Cauchy stress tensor is equal to a forcing right-hand side. Here you have to be careful. If you've never seen that before, it is the divergence of a matrix field, and this will give us a vector field. So this is a vector valued equation. We are in three-dimensional space, so there we have three components, and consequently also our forcing right-hand side will have three components. Then we have a constitutive relation, and as said, we will be solving linear elasticity, so the simplest constitutive relationship you can have. So a constitutive relationship is relating strains and stresses, and here we will speak in terms of engineering strains called epsilon, and we have our Cauchy stress tensor sigma, and the relation here is given according to this equation with the two parameters lambda and mu, which are the two Lamé parameters. And then we also have a relation from displacement to strain. Our displacement vector will be u. This one is a vector field that describes how a point in our structure is displaced under the given load. And the engineering strain tensor epsilon is just the symmetric part of the displacement gradient. So we will take the displacement gradient at the transpose displacement gradient and take the half of it. And although it might not directly visible, but the primary unknown in this system is the displacement vector. We could potentially plug everything back into the Cauchy momentum equation and then have one long equation where just u appears. But here I want to keep that separate such that we more clearly see what components are involved. As you've already seen in the intro, we have this clamped cantilever beam. The left end of our cantilever, so the entire face on the left, will be clamped. And clamped, of course, refers to a homogeneous Dirichlet boundary condition, because on these particular positions, our beam is not allowed to displace. So we will set the displacement to 0, and since the displacement is our primary unknown, we will set the primary unknown to 0, and that's an homogeneous Dirichlet boundary condition. And then there is a volume force, so in essence this F here, which is applied throughout our entire domain, and the domain is the beam, and this is a force due to gravity because the material has a certain weight to it, and this one makes our beam deform. In order to solve our problem with FEniCS, we have to translate our main partial differential equation, so the momentum equation, into weak form. And the weak form looks as following, in that we introduce a test function v, and recall, since the u is the primary unknown is a vector field in 3 dimensions, the test function will also be a 3-dimensional vector field. And the weak function then reads that the Cauchy stress tensor is in an inner product with the gradient of our test function, and then on the right-hand side, we have the inner product of the right-hand side with the right-hand side of the original PDE with the test function, plus a traction vector with the test function. This traction vector arises if we potentially had inhomogeneous Neumann boundary condition, but here all the other faces of our beam will just be free, so there won't be any additional load to it, so the traction vector is 0 on all of them. So actually this term will just vanish. But I want to keep it here for generality. If you want more details on why the weak form is that particular way, then please watch the next video where we're going to derive that in great detail. We're going to use an alternative form So this is the one that you would arrive usually if you make the classical steps of getting to a weak form, but we can equivalently write that, the left-hand side at least, as the inner product of the Cauchy stress tensor with the epsilon strain tensor, but not based on the actual displacement u, but the test displacement v. And the reason for this is that the sigma Cauchy stress tensor will always be symmetric, and therefore we only have to consider the symmetric aspect of the gradient of our test function, and this is equivalent to taking the engineering strain of it. So in essence, this is what we're going to translate into FEniCS and then solve for u, because u is the primary unknown. And then in the later on visualization, we also want to have the von Mises stress. The von Mises stress is a scalar stress measure. And that is quite important because it's really hard to visualize stress tensors, which are 3x3 components. So it's usually helpful to compute this scalar stress measure. And we can do that in a sort of a post-processing step. Once we have our u, we can then compute the sigma again. And with the help of the sigma, we can evaluate the so-called deviatoric stress tensor. And with the deviatoric stress tensor, we can compute the von Mises stress according to this formula here by taking the inner product of the deviatoric stress tensor. And if you haven't seen that before, this double dot or this colon is a double contraction, which is essentially a scalar product for matrices. Well, let's get started with the implementation. Let's scroll down a bit. And first, let's import FEniCS as FE. And then we can define some constants. So first, I want to define the size of our domain or the beam. So I have cantilever length, and I want the length to be 1 unit. And I want to have the cantilever width to be 0.2 units. And since we have a square cross-section, this one definition is sufficient. Then we also need to define by how many discretization points we want to create our mesh. And here I want to say endpoints in length direction shall be 10 and endpoints in width direction shall be 3. So it's a rather coarse discretization here. Then let's define the parameters according to our constitutive relation. So we have the lame mu parameter, which shall be 1. And then we have the lame lambda parameter, which I want to set to 1.25. And the density of our material shall be 1 unit. And finally, I want to set the acceleration due to gravity to 0.016. And these values might seem a little bit off. And the reason for this is that we are working in some sort of a scaled version. And this particular acceleration due to gravity ensures that we kind of get an reasonably small deformation such that our assumption still hold. Okay, then let's define a main function and leave it empty for a second. Then let's implement a main switch. So if name is equal to main, then execute our main function. Then we're sure it's only executed with the Python interpreter. And then the first step here is to define the mesh and the vector function space. And for the mesh, we're going to use the FEniCS box mesh command. And this box mesh command requires us to provide 2 points that define the smallest and the largest point of our cantilever. So we will start with a FEniCS point that is at the origin, so at 0, 0, 0. And then we will have a FEniCS point which is at the cantilever length, the cantilever width, and the cantilever width. And then we have to tell FEniCS by how many discretization points we want this to be discretized in space. And this, of course, shall be endpoints length, endpoints width, and endpoints width again. Then we can use this mesh in order to create a vector function space. So we will say FEniCS.vector function space, and this first requires us to hand over the mesh. Then we have to define the family, and this will be the family of elements we're going to use. And the simplest one here is just going to be the Lagrange family for us. And we will set it to degree 1, which gives us linear ansatz functions. And I also want to give this function space a really verbose variable name. So it shall be Lagrange vector space first order. And now we have our function space created. Then next up, let's define the boundary conditions, or more precisely, the one boundary condition we have. And so recall, we have our beam clamped, or our cantilever clamped on the left face, and all the other faces are going to be free. So theoretically, there would be a zero traction vector. We will consider that later, but we only have to consider the Dirichlet boundary conditions here. So let's create our Dirichlet clamped boundary. So let's say Dirichlet clamped boundary, and we need FEniCS.Dirichlet boundary condition for that. And this first requires us to hand over the function space, and then we have to define the value on the boundary. And since we want to have an homogeneous Dirichlet boundary condition, that is of course 0. But since we have a vector space, it has to be vector 0. So it will be FEniCS.constant, and then the argument will be a tuple with 0, 0, 0. And then this requires us to provide a boundary Boolean function. So we have to tell FEniCS on which of the boundaries that is valid. So right now FEniCS would think that it's valid for all the boundaries, but here we just want to have it on the left. So let's create a function which I want to call clamped boundary. And this one takes 2 arguments, or this is the signature that FEniCS wants us to implement, which is an x. So the current position FEniCS want to query the boundary condition, as well as an on-boundary flag. So FEniCS will tell this function, or it will call it at certain points and say, hey, I'm on the boundary with this particular position. What type of boundary is it? And we only want this function to be true if we are on the left face. So we will return a logical expression with on boundary and x0 being smaller than dolphin epsilon. I mean, usually you would say x0 had to be 0 because then the x0 axis was 0 and we are on this face. But in order to avoid rounding errors, we will just use a small epsilon here, sometimes like 10 to the minus 14 or so. And this function can then be handed over to our Dirichlet boundary constructor. And let's do that. And here we go. That's the Dirichlet clamped boundary. So next up, I want to define helper functions, which essentially translate what we had here, so the constitutive relation, as well as the displacement strain relation. So let's get down here and implement stress and strain. So define strain and stress. So it makes more sense to have it in that particular order. So let's define epsilon, or the engineering strain, which depends on u, which is the displacement field. So we will get the engineering strain, which is going to be 0.5 or 1/2 of the sum of the regular gradient of our displacement field and the transpose gradient. So we will say FEniCS.gradient on u plus FEniCS.gradient on u dot t for the transposed version. However, here we have to be a little bit more careful. So FEniCS is following the definitions in multivariate calculus quite closely. And once we have non-scalar fields, so this is a vector field, the idea of a gradient becomes a little bit ambiguous. So in order to get the correct gradients also in higher tensoric objects, here it would be reasonable to use the so-called nabla gradient. So we have a nabla gradient here. The details might be a little bit small-grained. I will leave a link down in the video description if you want more details on why it should be nabla gradient and not gradient. Okay, then this epsilon function should return this engineering strain, and then we have our epsilon implemented. Then let's move on and have the Cauchy stress. So define sigma on u, and this shall be translating the constitutive relation. So let's look at it. So we say that the Cauchy stress tensor is given as 2 times mu, so the Lamé parameter, times the epsilon strain tensor. So this is a 3x3 matrix, and this will just be 2 scalars multiplied with it, and this will be the first component to our sigma stress tensor. And the second component is given by taking the trace of the epsilon tensor. So the trace is the sum of the elements on the main diagonal. multiply that with lambda, so this will just be a scalar, and then multiply that with the identity tensor, and I gave it a lower index 3 because it's the 3 by 3 identity tensor, so it's a matrix in that sense. So then in the end, our addition is again well posed, so we will get our sigma. Okay, let's translate that. Going down here and say we want to define the Cauchy stress. And the first component, so the one with the trace, let's have that one. So we have the lambda multiplied with FEniCS.tr for trace on the epsilon of u. And then we multiply that with FEniCS.identity 3 in order to get the 3 by 3 identity matrix. Then we add 2 times mu multiplied with epsilon on u. And then this function just has to return this Cauchy stress and we're good to go. And with the epsilon and sigma done, we can then define the weak form. But before we can do that, we first have to instantiate trial and test functions. So I want to get u trial, which will be the representative of the primary unknown in our PDE. And for this, we will say FEniCS.trial function on our function space. And then we need a vtest function. So FEniCS.test function on the Lagrange function space. Well, then let's take a look at the weak form again. So we want to have this alternative form here. And then we also need F and T. So the forcing vector as well as the traction vector. So let's do the forcing vector first. So let's say forcing is going to be Fe.constant. This one has the following components. It will be 0 in x direction, 0 in y direction, but it will be minus density times acceleration due to gravity in z direction. And recall, this is a volume force, so it acts within the cantilever. And this shall represent the weight that this cantilever has. And of course, this should be pointing in the direction of the gravity, which will be the negative z-axis here for simplicity. Then let's also define the traction, which shall be FEniCS.constant of 0, 0, 0. And that's just here for generality. If you had Neumann boundary conditions, so in other words, like surface forces, that had to be accounted in this traction vector here. Then we can define the weak form left-hand side. So in essence, this will just be what we have here on the left-hand side. So the inner product of the Cauchy stress tensor based on the actual displacement u, or the trial as the representative of the unknown, together with the epsilon engineering strain based on the test displacement. Okay. So we will have the weak form left-hand side as FEniCS.inner on the sigma based on u trial with epsilon based on vtest. And then we multiply that with FEniCS.dx in order to show that this is the integral, because here it is the vector inner product, or more precisely the matrix inner product, so the colon operator, whereas here this is the functional inner product, which already includes the integration, but here we have to add it with the FEniCS.dx. Then we have our weak form right-hand side, and for this we first have the contribution from the original volume forcing, which will be FEniCS dot product between F and V multiplied with FEniCS.dx, and F was the forcing and V was vtest. And then let's just add, as that for generality, the product between the traction and the test function. So FEniCS dot and then traction and vtest and multiplied with Fe.dx to represent the integration over the domain. And now you might ask yourself, hey, why do we use dot here and why do we use inner here? To be fair, here we could have also used inner, because the inner product between two vectors is the dot product between those two. So that one is equivalent. However, here we have to be careful because here we could not use dot because the dot product between two matrices, or these tensors in that sense, is not the inner product. So I just want to leave that here as a comment and say this is crucial to use inner and not dot. If you were to use it, you would get an error here. That is because in the weak form, we always have a contraction down to scalar values. And we can only achieve that by using the inner product between two matrices. Now we have everything modeled and can solve the weak forms. So this is rather straightforward with FEniCS. So I want to call this step compute solution. For this, we first have to instantiate our solution field. So uSolution is going to be FEniCS.function on our function space, because trial and test functions, these are used in order to represent our weak form, but this will be a variable where we can actually store our fields in. And then it's just a call to FEniCS solve and say weak form left-hand side is equal to weak form right-hand side. And then we can save the solution in uSolution, and we want FEniCS to respect the Dirichlet clamped boundary condition. And what FEniCS is going to do under the hood is to first compile our weak form, because here there are some nested expression, because we have this function call to sigma, to epsilon, and then within sigma we have a call to epsilon. So in the end, the FEniCS implementation will compile down this weak form, and in essence will do what we could have also done by just inserting all the nested dependencies into the momentum equation. And then it assembles the linear systems of equation. It considers for the Dirichlet boundary conditions and then calls an elegant linear solver, hopefully, in order to get our node-wise solution. And that's already good, but we also want to have the post-processing step with the von Mises stress. So we want to compute the von Mises stress, and let's look at the algorithm again. So the first step was to compute the deviatoric stress tensor, and for the deviatoric stress tensor we take our Cauchy stress tensor and subtract a third of the trace and just put it into the identity tensor. Okay, so we will have the deviatoric stress tensor is going to be the sigma applied to our uSolution, and then subtract 1 divided by 3 multiplied with FEniCS.trace on the sigma of uSolution multiplied with FEniCS identity 3 to get the 3 by 3 identity matrix. And then finally we have the von Mises stress, which is FEniCS.square root on 3 divided by 2 multiplied with FEniCS dot, and now we have to be careful. Let's go back up. Here we have the colon, so the double contraction, and that's said, this is the scalar product for matrices. So let's do inner product between the deviatoric stress tensor with itself. So let's have FEniCS dot inner on the deviatoric stress tensor with the deviatoric stress tensor. And now you might say, okay, hey, this is our solution field. That's actually not the case, because similar with the actual FEniCS solution, it first has to be compiled by FEniCS, and we can force the compilation by projecting this hypothetical field onto a function space. You might say, okay, we already have a function space, but here we have to be careful. This one is a vector function space, whereas the von Mises stress is a scalar field. So we have to create a new function space, which is in terms of a scalar. So let's create a Lagrange scalar space, and also let's have it first order and say FEniCS.function space on the mesh with Lagrangian elements of order 1. And then we can get the von Mises stress, and I will just override the variable here by saying FEniCS.project the von Mises stress, so this UFL, the unified form language expression, onto the Lagrange scalar space first order. Last but not least, let's write out the files into a format that Paraview can understand. So let's call this write out fields for visualization with Paraview. FEniCS also comes with some capabilities of visualizing in 3 dimensions, but I believe that this one is better done with Paraview. So for this, I first want to rename the fields here, because then they have proper names in Paraview. So let's say use solution.rename and then call this the displacement vector without any description. That's fine. So an empty string here. Then the von Mises stress, let's also rename that one into the von Mises stress without a description. And then let's create a beam deflection file pointer by saying FEniCS dot, and now there are a couple of options. Here, if we want to save multiple fields within one file, it's usually helpful to use xdmf file and call this the beam deflection.xdmf. And then let's just add some options here. So let's say beam deflection file.parameters and say flush output to correctly write the file to be true, and beam deflection file, let me scroll a bit, .parameters, and then say functions share mesh being true, because the von Mises stress as well as the displacement are based on the same mesh. Those are just, one is a vector field and one is a scalar field. And then we can write it out by saying beam deflection file dot write u solution and then at 0, 0. That's because those files usually allow for transient simulations, but here we computed a steady state, so we just be at time step 0. That's absolutely fine. And then beam deflection file dot write von Mises stress at 0, 0. And hopefully we didn't make any mistakes. Let's check that. Let's bring up a terminal and then execute Python cantilever beam linear elasticity. And here we see it's calling the just-in-time compiler, solving it, no errors. Let's hope everything went smooth. And if you then open the file explorer, you see that you have 2 additional files in here, the beam deflection.h5 as well as the beam deflection.xdmf. I now opened up Paraview, and then you have to click in the top left on this icon in order to navigate to your folder where you did your simulation, and then select the XMF file. And then for me, asking what kind of reader it wants to use, and the default one here is fine, so I click OK. And then you see we have the beam deflection.xdmf loaded into our pipeline browser, and we see we have 2 arrays, or in other words, 2 fields, the displacement vector as well as the von Mises stress. So let's click apply in order to get something here, and then you can use the left mouse, hold it and move it around in order to swivel. Here we basically get a box with the von Mises stress going from 0 to 1, and here we see that this might be the clamp edge or the clamp face, because here we have the highest von Mises stresses, whereas we are stress-free at the other end. Okay, so now I want to do a couple of filters. First filter, let's go to filters and then hit search and search for warp by vector in order to show us how the displaced state looks like. Move to it, hit enter, and then you get another entry in your pipeline browser. And here you should be using the displacement vector as your warping vector. Use a scale of 1 and then hit apply. And now you see it has a little deformed, so I kind of have to maybe move it like this, such that we see. So we have our clamping here. The forcing was as set in negative z direction, and now our beam is displaced. We colored the displaced state with the von Mises. Let's maybe go to the beam deflection, to this one here, and change the representation to outline, and then use the eye icon to the left in order to reactivate it. And now we also see the reference state. Keep your beam deflection highlighted and then hit filters, search again, and go for cliff. And I want to use arrows in order to show our displacement field. And I want to be oriented by the displacement vector. I want to be scaled by the displacement vector, and I want to have a scale factor of 1.0. And then there is also the option to color it. I mean, we will see it in a second. Let's hit apply. And now it's everything blue, and I want it to have no color. So I will just use solid color. And finally, we arrived at our final visualization. So we see, of course, that towards our clamped edge or directly on the clamped edge, we don't have any displacement. So there, the displacement vector is 0. Whereas at the end of our clamped beam, we have the highest displacement, so the longest displacement vectors. And you also see what a displacement vector means. If you go closely, then this particular point in the reference configuration has been displaced to this position, and the arrow is the difference between the two. And then, of course, we also see the von Mises stress. Feel free to play around with it. You can download the source code file from the video description, and I think there are many interesting things to do with it. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. Thank you so much for watching this video. If you enjoyed it, then please consider liking the video and subscribing to the channel. There are more FEniCS tutorials like this, and also more FEniCS videos, like the follow-up video, where we will derive the weak form in great detail. Here you will now see similar videos, and I hope to see you in one of the next videos.